Today we're going to carry on our discussion on different applications of quantum mechanics. In the previous lecture we've seen lasers, we've seen Doppler cooling, which is one of the methods of using lasers to cool atoms in a gaseous state. Today we're going to look at an exciting concept that's also related to cold atoms. You need to pay special attention to this because you not find this in topic in most modern physics textbooks or in quantum mechanics textbooks. It's a specialized topic. So what I would like, but before that I would like to talk a little bit about identical particles. Now suppose I have a quantum dot A and another quantum dot B. The levels inside this quantum dot, they are quantized. This is an infinite well. Here I have an infinite well. And I take an electron and I put it inside quantum dot A, the infinite well A, and then I take another electron and somehow load that electron into quantum well B. Now these two electrons, first of all, they are identical particles, totally identical, which means that both of these electrons have the same properties whatsoever. They are exactly identical in their mass, they are exactly identical in their charge, they have the same spin. Electrons have spins as well. So you cannot tell if you have a bunch of electrons, all of them are they are identical, perfectly identical. However, you have placed the two electrons into distinct wells. Which means that I can identify well A from well B. These wells can be spatially separated. They can be in different locations of space. For example, if I want to build a MOSFET kind of device, I have a source, I have a drain. I can engineer an island of a semiconducting material here, A, and I can engineer an island of a semiconducting material here, B. So A and B are at distinct locations inside this transistor. So even though I have identical electrons, I am putting them in distinct locations. So I can tell which electron is in A and which electron is in B. So even though the particles are identical, but the electrons, even though they are identical, they are distinguishable. I can distinguish an electron in A from an electron in B because I can selectively address these wells separately. I can talk to this electron without having to talk to this electron. I can put a field on this electron or put a voltage on this electron, so I can have a gate here and I can have a gate here and I can apply a voltage here VGA and I can apply a voltage here VGB. So when VGA is applied, if this dot is far away, it's not affected by VGA. So I can selectively talk to and address the individual electrons. So even though the electrons are totally identical in all respects, the electrons are distinguishable. I can distinguish one electron from the other. Alright, so these electrons are identical but distinguishable. But in most cases in nature, in quantum mechanics, you don't have this luxury of distinguishability. For example, take the hydrogen molecule. The hydrogen molecule, if I were to draw a cartoonic picture, it has 2 protons and 2 electrons that are shared between the 2 protons. So the electrons form a 1s bond. So if I were to draw a cartoonic representation, there's a cloud of electrons. There's a molecular orbital, a 1s molecular orbital. You studied molecular orbitals, I imagine, and I took this information from the chemistry lecturer. He taught you about molecular orbitals. Is that true? So there's a molecular orbital, and there are 2 electrons inside this molecular orbital. And those 2 electrons are being shared by the 2 protons inside a hydrogen molecule. Now those electrons are identical. All electrons in this universe, they are all identical. You cannot, one electron is no different from another. But in this molecule, not only are the electrons identical, they are also indistinguishable. Because as you know, quantum mechanics is the supreme law of nature at this level. You cannot take a microscope and track the individual trajectory of a single electron, because there is no trajectory of a single electron. The electron is actually a wave function, right? And the wave function is spread over, and here the 2 wave functions, the 2 electrons are overlapping in a massive fashion. So you can't tell one electron from the other. So in this case, the 2 electrons are indistinguishable. They are indistinguishable. You cannot tell one electron from the other. You cannot track the motion of a single electron, keep an eye on a single electron, and forget about the other one, because the 2 electrons share the same space. They have wave functions that are mutually overlapping. And if you have 2 wave functions that are mutually overlapping, you get a superposed wave function. And you cannot tell which wave function belongs to which. The 2 electrons are totally indistinguishable in this case. So here I have an example of indistinguishable electrons. Let me give you another example. I have a solid, and a special kind of a solid that is called a metal. And a metal, we all know, conducts electricity. Who is responsible for the conduction of electricity in a metal? Which entity? The electrons. Which atoms do these electrons belong to? To which atom? To the core atoms inside the metal, but these electrons are freed from the atom. These are free electrons. They don't belong to any atom. So now what you have inside the metal is an array, matrix of positive ions called core ions, and the valence electrons, the ns electrons, which are in the s orbital of these electrons, they have been rendered free. They have been stripped out from these atoms, and now they're wandering around in the metal. So you have a sea of electrons, which means that the wave functions of these electrons, they are spread out over the entire volume of the metal. And you cannot tell which electron is which. All of these electrons, all of them belong to the same solid, and they are indistinguishable. You cannot track a single electron inside this solid because their wave functions are all overlapping. So this is another example of indistinguishable identical particles. So why am I emphasizing indistinguishability? I'm emphasizing indistinguishability because it has profound consequences for nature, for how this world operates. In fact, if I look at indistinguishable particles, they are all particles in this universe, they can be lumped into 2 types. There are only 2 kinds of particles. One of these particles, one of this class, are called fermions. And the other class of particles, they are called bosons. Fermions is named after an Italian physicist, Enrico Fermi, and bosons are named after an Indian physicist, Bose. So there are only 2 kinds of particles, indistinguishable particles in the universe. Fermions and bosons. Bosons are like birds that like to flock together. I'll explain what this means. Fermions like to remain separate. I'll explain what this means. But what are these bosons and fermions? You've all come across the Pauli exclusion principle. The Pauli exclusion principle also derives from what I'm going to explain in a minute. Okay. Now suppose I have two particles, particle 1 and particle 2. And these particles are indistinguishable. Particle A is in a quantum state. I call this state phi. This is a wave function for particle number 1. Right? You're all familiar with wave functions. I don't have to harp upon the same tune over and over again. It's just the wave function. The wave function for particle number 1, it could be an s orbital, a p orbital, any wave function, any state for particle 1, quantum state. I could also write this, by the way, as phi for particle 1. Okay, this is the quantum state, but here I choose to write it in wave function form. Wave function or state of particle 1 is phi. The state of particle 2 is chi. Just using a symbol. Okay? So let's call this combined state of particle 1 and 2, let's call it psi. So this is a state of both of the particles 1 and 2. Now just as a mnemonic means just as a visual aid, a conceptual aid. Don't take this literally. I have particle 1 and I have particle 2. Particle 1 has some wave function phi, and here I am drawing, say, an electron cloud. And particle 2, which is an identical particle, an indistinguishable particle. So both of them are electrons in the same region of space, or protons in the same region of space. So this is my mnemonic, don't take this literally, this is just a picture, visualization of what I've written over here. Now if I ask you to close your eyes, and I take particle number 1, there is some omnipotent being, some supreme being, for example, who can hold this particle 1, your eyes are closed, and 1 and 2 are exchanged. The particles are swapped. Then I ask you to open your eyes, you will see no difference whatsoever. You can't tell the difference whether such a swap has been made. Okay? So if I were to exchange these particles, which means I would like to have a new wave function, swap, I would like to swap this, which means I swap 1 and 2. Which means, let me write this as 2, 1. The swapped version of 1, 2. Now this means that particle number 2 is in state phi, and particle number 1 is in state chi. I can't tell the difference, but the wave function, the state has changed. This state looks different from this state. Okay, so what I've really done is, let me draw this with a pink color. Even though these are indistinguishable particles, I'm just trying to make a point here. I can't draw yellow and pink. So what I now have is 1, wave function 2, same amoeba kind of picture here. Number 1, this is 2 here, and this is 1. So I exchange the particles. I've done an exchange operation, a swapping operation, or a parity operation on these particles. And these are totally indistinguishable particles. Now I get a new wave function. Alright. Now, what's the relationship between this transformed wave function and the original wave function? What's your idea? Should they be the same or different? how should they be interrelated? Should they be just the same? These are indistinguishable, identical particles. Any guesses? Same? Yes? Just the same? Exactly the same? Alright, so experiments tell you that you can't measure wave functions. You can only measure the modulus square of wave functions. So, if I were to perform some position measurement operation on this state and on this state, I will get no difference whatsoever. So what is unchanged is the modulus square of the wave function. The physics doesn't change. The realizable physics doesn't change. All measurements remain the same. Okay, now measurements are embodied, they are encapsulated by probability density. So the probability density of locating the particles in this region of space should not change whatsoever. Which means that the probability density associated with this state must be identical to the probability density associated with this state. This means that psi 1, 2 modulus square must be psi 2, 1 modulus square. Okay, because the physics doesn't change, the measurement outcomes don't change. The measurement outcomes depend upon the probability density. They don't change whatsoever. Okay, because these are indistinguishable identical particles. Now if I look at this relationship, the two are interconnected. The modulus squares are interconnected. Now what about the wave functions themselves? If I were to take the square root of both sides, what do I observe? If I took the square root of this, psi 1, 2, square root is of course this square root is of course this, but do I have the liberty to choose a sign here? I could have a positive sign or I could have a negative sign. So there are two conditions, there are two possibilities for these particles, and only quantum mechanics has the beauty and the aesthetics to actually give you such a result. This cannot come out of classical mechanics. This is quantum mechanics that is equating probability densities and then downgrading the modulus squares to just the normal bare wave functions and inserting these positive and negative signs. If you take the modulus square of both of these terms, left and right hand side, you get this. So this is a legitimate expression. So there is the possibility of having a positive sign here or a negative sign here. What does the positive sign mean? The positive sign means that if I exchange the particles, the wave function does not change. If I have two indistinguishable identical particles for which the exchange does not change the wave function, or for which the wave function is symmetric under exchange, then such particles are called bosons. And if I have a wave function which changes sign under exchange of particles, then those particles are called fermions. Just a minute. So bosons are symmetric under exchange. And fermions are anti-symmetric under exchange. And all particles in the universe could be the fundamental particles, electrons, protons, could be atoms, ions, nuclei, quarks. All of these particles are either belong to the category of bosons or they belong to the category of fermions. Electrons, protons, neutrons, they are fermions. Carbon-13 nucleus, is a fermion. Nitrogen 15 nucleus is a fermion. Photons are bosons. W particles, they are bosons. Helium nuclei, they are bosons. Alpha particles are, so all of these particles fall into one of these two categories. Question? There was a question, yes. Yes, so we can measure this thing. We'll come to that. Yes.
So in the starting cell, bosons locked together by fermions are choose to be separate in states. What does that have to do with the signs? What does that have to do with phosphor?
I'm coming to that next. Yes.
So why didn't we place a plus minus next to psi 1, 2?
Plus minus here?
The other side.
Sorry, मैं समझा नहीं बात है.
Why don't we have a plus minus next to psi bracket
Here?
1? Yes, over here.
You can either have it here or here, it doesn't matter. या यहाँ लिख लो या यहाँ लिख लो.
Okay.
Yes. Why does a swap take place? So you performing an operation, a swapping operation. So these particles behave differently under the swapping operation. The fermions behave antisymmetrically and the bosons behave symmetrically. So you would like to see how your wave function transforms under different kinds of transformations. Particles are defined by how they behave or respond to transformations. If you take a mirror image, what happens to the particle? If you translate it or rotate it, what happens? This is how we define particles. So swapping is one operation that helps us distinguish between the two kinds of particles. Now, how does the Pauli exclusion principle is in fact a corollary, a deduction of this general principle, which is also called the Pauli principle. So what I've described here is lumped under the term Pauli principle. So the Pauli principle, the Pauli exclusion principle is a strong version of the Pauli principle. I'm going to explain this. But any questions about fermions and bosons, about this central result? Yes? If I have a wave function psi, I have two particles, 1 and 2, and I exchange the particles, which means I perform an exchange operation or a swapping operation, okay? Which means I can write, let's write the swap wave function as 2, 1. If this is equal to the original wave function, this means that the wave function is symmetric under exchange. Okay? Symmetric or even under exchange. Okay? And if the wave function as a result of the exchange is negative of the original, it picks up a minus sign, then such a wave function is called anti-symmetric under exchange or odd under exchange. Okay, so this is a definition. This is how we define symmetry. Yes. Let me give you, so this is mathematical at this moment. Let me give you a physical implication of this. Okay, so that the physics comes through. Okay, any more questions? Yes. Yeah, you can. Yes, you can do that. I've uploaded a paper on this website, which is called the Heisenberg Microscope. The Heisenberg Microscope actually takes pictures of the electrons inside orbitals inside a hydrogen atom. It puts the hydrogen atom in an intense electric field and puts the laser light, the electrons come out, and by looking at the position of the electrons that are coming out, you can find out what the original position of the electron inside the atom would be. So you can image wave functions. Yes? Alright, so a corollary of this. If I have particle number 1 in a state phi and particle number 2 in a state chi, is this wave function, as I've written it, is it symmetric or anti-symmetric? Is neither. If I were to swap the particles here, what would I get? I would get the second particle in the state phi and the first particle in the state chi. Now this is neither the same as the original and it's neither negative of the original. So the way in which I've written the wave function here is neither symmetric nor antisymmetric. But for fermions and bosons, the wave function has to be either symmetric or antisymmetric. If I take two particles, their wave function must fall into one of the two categories that I've defined. It has to be either symmetric or antisymmetric. Now how can I construct a wave function of two particles which is, say, antisymmetric? I would like to construct, I have two fermions, I would like to construct an antisymmetric wave function. Since I'm constructing an antisymmetric wave function, I immediately know I'm talking about fermions. So how can I construct an antisymmetric wave function? I'll give you 2 minutes to think about this. Just starting hint starts with this. I would like to make a state of two particles which is antisymmetric under exchange. Don't talk about axes, talk about chi's and phi's. I have this, how can I construct? Let me give you a hint. I start off with this and I would like to make a superposition of chi and phi such that the overall wave function is antisymmetric under exchange. I give you 2 to 3 minutes to think about this. Write it down on your notes. After my question. Keep in mind, this is neither symmetric nor antisymmetric. This gives me this, and this is not related to this. It's neither plus this, neither negative of this. So I want to construct an antisymmetric wave function. What's the simplest wave function that you can think of? Think in terms of superpositions. Quantum mechanics gives you this liberty of creating superpositions. You cannot have it in any other philosophy, in any other theory. It's only quantum mechanics that gives you this luxury. You're on the right track. Let me write down the wave function. The first particle in a state phi, the second particle in a state chi, minus the second particle in a state phi, the first particle in a state chi. And if I am really careful, if I am a Puritan, I would like to normalize this, but it's unimportant. So look at this wave function here. It's a valid wave function. It's a position. It's the first time you're encountering two particle wave functions, by the way. Now if I look at this wave function and I perform the swapping operation, I swap the particles. Okay? Which means that I am constructing this swap version of the original wave function. Let's perform the swap. Swapping here means that the second particle is in a state phi and the first particle is in a state 1. So I perform the swap operation on this state. I get this. This negative just carries over. Here, the second particle is in a state phi. I would like the first particle to be in a state phi and the second particle to be in a state chi. So I swap the two, I've exchanged the two particles, and now I have generated a new wave function. How is this new wave function related to the original wave function? It's the negative of the original. So this is the negative of the original. Hence, if I have two fermions, this is the wave function of the two fermions. Because the wave function of the two fermions has to be odd or antisymmetric under exchange. This is the wave function that is antisymmetric under exchange. So this is the wave function for fermions. So if I have in a helium, in a hydrogen molecule, the two electrons will have this wave function because they are two indistinguishable fermions. Now the Pauli exclusion principle automatically spills out of this automatically. But the Pauli exclusion, any questions about this? Do you agree this is antisymmetric under exchange? Yes. G. The wave functions. We're not converting anything, we're writing down the wave function for fermions. This is not the wave function for either fermions or bosons. Okay? So now, I hope you understand this. What, क्या समझ में आया? ये कैसे आया? ये कैसे आया? ये चीज? I wrote down a wave function. I have to be creative. I have to use my creative license. I write down the wave function. Okay, I propose that this is my wave function. Okay, you don't derive everything. You have to be creative as well. So I'm trying to be slightly creative because thousands and hundreds of thousands of people have written down this wave function. They told me that this is the wave function. So I write it down and I verify that this wave function is antisymmetric under exchange. Okay? Now the Pauli exclusion principle just trickles out from this antisymmetric form of the wave function. The Pauli exclusion principle states that if I have two fermions, they can't be in the same quantum state. That's the Pauli exclusion principle. Two fermions can't exist in the same quantum state. Now how does this come out from this? If the two quantum states are the same, this means that in my description here, phi, I'm proposing that phi is the same as chi. If my phi is the same as chi, then the wave function just disappears. Wave function goes to 0. If phi equals chi, this becomes phi, phi, phi 1, phi 2, phi 2, phi 1, just 0. So the wave function disappears, which means that fermions cannot exist in a state in which both of those fermions have the same quantum state. Okay? So this is the Pauli exclusion principle. It stems out of this Pauli principle. The Pauli principle is the bigger version. And the Pauli exclusion principle is just the application of the Pauli principle to fermions. So if this is true, then my wave function just disappears. So which means that the electrons or fermions cannot exist in this state. The Pauli exclusion principle has profound consequences. Likewise, I can also create, if I have two bosons, I would like to have a symmetric wave function. Okay? Can you, now immediately you can tell me what a symmetric wave function for bosons is going to be. So this is for bosons, this is for fermions. Can you tell me what a symmetric wave function, a candidate symmetric wave function could be? Just the plus sign. I replace this minus with a plus. Phi 1, chi 2, plus phi 2, chi 1. This under root 2 just carries on for the right. It's just for normalization. It doesn't change the physics. So this is a symmetric wave function. And bosons can exist in this state, over two bosons. Now, I hope I've actually demonstrated. Let me give you a simple example. Yes. No. All fermions in this universe are identical and they have different quantum states. Identical means that they have the same properties. They have the same mass, they have the same charge, all of them are spin half particles. That is what is meant by identical. Indistinguishability means that if you have a swarm of electrons sharing the same space, you cannot track one electron and not look at the others. Okay? This is what is meant by indistinguishability. And what does not having the same state mean? For example, I have a helium atom. And this is a 1s orbital inside a helium atom. Now I have two electrons inside the helium atom. If one electron is in this orbital, which means that this electron has three quantum numbers, n, l, and ml. n is 1, l is 0, ml is 0. So this electron has these three quantum numbers, but it's indistinguishable with another electron inside the same orbital. Now this electron also has the same three quantum numbers, but there's another quantum number. That Schrodinger equation is devoid of that. The Schrodinger equation cannot predict the fourth quantum number. That comes from relativity, and that is called the spin. And I talked about the spin in one of the lectures. So one of the electrons will have a spin that points in one direction, and the other electron has a spin that points in the other direction. So this electron has a spin quantum number of plus half, and this electron has a spin quantum number of minus half. So the quantum states are different because one of the quantum numbers is different. The collection of four quantum numbers defines the quantum state. But those electrons are identical, have the same charge, same mass, and they are indistinguishable. You can't tell one electron from the other. Now, if I have, so this is helium in its ground state. But but we can't tell which electron had that state. We can detect the state of electron, but we can't tell which of these electrons is giving us that state. Now if I have electron, if I excite the helium atom, for example inside a helium neon laser, we excite the helium atom. So there's a 1s, there's a 2s. This is the excited state. So now I can have an electron. The quantum numbers are now different because the n quantum number is different here. So this electron in the excited state could either have the spin parallel to the spin, so they have the same spin quantum numbers, or I can have an equally valid configuration in which this electron is pointing in the opposite direction. So there is no constraint on what the spin of this electron has to be because the other quantum numbers are different. So these two electrons have different quantum states. These electrons have different quantum states. Suppose I have lithium, 1s, 2s. The lithium in its ground state has 3 electrons. Now I would like to put in electrons inside these levels. So the first 2 electrons go inside 1s, but they must have opposite spins so that they satisfy the Pauli exclusion principle. Now where does the third electron go? It cannot go into 1s because either it will have a spin up and then it's going to be in the same quantum state as this electron, or it must have a spin down, then it will match the quantum numbers of this electron. So this third electron cannot possibly enter the 1s level. So naturally, just by quantum mechanics, just by the Pauli exclusion principle, the energy of this third electron goes up. And then it can go into the 2s orbital and can have a spin pointing in any direction. Naturally, you would assume that if you are at 0 Kelvin, all the electrons will go into the ground state, which is 1s. But now there is some special reason for an electron to be in a high energy state, just because of the Pauli principle. The Pauli principle, in a sense, is raising the energy of the universe. It's not allowing fermions to occupy the same state. It's pushing. This is real estate for the electron. They are fermions. You don't want to cramp or crowd more than 2 electrons in the same state. And even if there are 2 electrons, they must have opposite spins so that the quantum states remain different. This third electron has to be promoted to the next available level in the energy manifold. So naturally, the energy of this universe is going up because of the Pauli principle. It's an outward pressure on particles. They cannot be cramped into the same space because then they will have the same quantum states. You would likely have to have them different quantum states. So energy is gradually going up inside the universe. So this effect is seen at the quantum scale, nanoscale, as well as the galactic scales. It's a really important phenomenon. The Pauli doesn't come out of normal Schrodinger quantum mechanics. Okay. Yes. ऊंची बोले सबको आवाज है. Not necessarily. Even if this lithium atom were at 0 Kelvin, this degeneracy pressure, this pressure exerted by the Pauli principle is raising the energy. It's not coming from the surroundings. It's quantum mechanical. The origin is quantum mechanical. Yes, at the back. G. When a fermion and a boson interact, you see, when a fermion and a boson interact, I don't understand the meaning of interaction, but fermions interacting with bosons is really complicated. For example, an electron emitting a photon. So you study this in quantum field theory, but let me give you a simple example, a nucleus. In a nucleus, you have protons and neutrons. Protons and neutrons are fermions. Okay? But consider a helium nucleus. 2 protons, 2 neutrons. So you have two fermions which are protons and two neutrons which are also fermions, but overall the nucleus is a boson. It has spin 0. So these fermions congregate and they can form new particles which could be fermions or bosons. A carbon-12 nucleus, 6 protons, 6 neutrons is a boson. But a carbon-13 nucleus, which is an isotope of carbon, is a fermion. It has 6 protons and 7 neutrons. All of them are fermions, but they combine together to give a nucleus which is a boson. And in fact, the best way of choosing between a boson and a fermion is to look at the spin. The spin tells us whether a particle is a boson and a fermion. A boson has spins S equal to 0, 1, 2, 3, and so on. And a fermion has a spin which is 1/2, 3/2, 5/2, 7/2. So odd multiples of 1/2. So this is how to distinguish between bosons and fermions. Now how can you tell if I have a particle of some spin S and a beam of particles, and I want to tell whether they are fermions or bosons, which means I would like to find out the spin. What kind of experiment will I devise? I've already discussed this experiment in one of the early lectures. What kind of physical arrangement or experiment can I build to distinguish, to tell the spin of this beam of particles? The Stern-Gerlach experiment. I put in an inhomogeneous field. Excellent. An inhomogeneous magnetic field. The inhomogeneous magnetic field will split up this beam into some components, some number of components. It will actually split up this beam into 2s plus 1 components. If s is 1/2, it will split up this beam into 2 components. If s is 1, it will split it up into 3 components. If s is 3/2, it will split it up into 4 components. And each component is the projection of the spin along the z-axis. So, suppose s equals 1. Then my ms, which is a quantum number, could be 1, 0 or -1. One of the beams corresponds to ms plus 1. The other corresponds to ms 0. The third one corresponds to ms minus 1. Okay? So by looking at the number of beams that this incoming beam is split up into, I can tell what the spin of the particle is, and I can distinguish between fermions and bosons. In fact, bosons and fermions are distinguished easily by looking at the spin, by measuring their spin. And this experiment takes place because the spin acts like a tiny magnetic moment. We've seen that. Please refresh your memories on that. Now suppose I have an infinite well, and I'm drawing 2 infinite wells here, in which there are some energies. Let me draw 2 harmonic oscillators. 2 harmonic oscillators, so that I can draw equally spaced levels, just for clarity. So this is not an infinite well, because in an infinite well the levels are not equally spaced. For clarity on the blackboard, I'm actually drawing a harmonic oscillator in which the levels are equally spaced. Okay? So I'm drawing 2 harmonic oscillators, and these are the energy levels, the rungs of the ladder. So these are energy levels. And suppose I'm at 0 kelvins. So there is no energy provided by the environment, man. No energy provided by the environment. It's a cold, frigid environment. No energy whatsoever. Assume you don't have the 0-point energy. So it's cold, frigid environment. And I have a collection of fermions. A collection of fermions. And I would like to populate those fermions inside this harmonic oscillator. So this is a level that is a receptacle for fermions. I would like to populate fermions in this. And I've drawn this as a receptacle for bosons. So I would like to put bosons in here. First of all, let's consider the fermions. I want to put fermions inside these levels. So I start off with the lower energy state. That's what nature likes. You always start off with the lower energy state. So I put an electron in the lowest energy state. And I put two of them in the lower energy state. And I assume that they have opposite spins. So one is spin up, one is spin down. I don't want to draw the spins because that will clutter the diagram, but they are opposite spins. So two of them go into the same level. And both of these electrons have the same energy. So they are degenerate electrons. Different wave functions because different quantum states, but the same energy. So they are degenerate electrons. The next two electrons go into the next level. Now what is making these electrons go into the higher energy level? It's not the energy available in the environment, it's the pressure of the Pauli principle, of the Pauli exclusion principle is exerting a pressure which is raising the energy of these electrons. It's pushing away the electrons. These fermions don't want to stick together. They have to go into different quantum states. And the only quantum states that are available are higher energy levels. Let me finish, please. So these keep on populating these harmonic oscillator manifold. And suppose I give you a number of electrons, some number of electrons. So they keep on populating, and when the electrons just finish off, that's what our population distribution of the fermions inside this energy structure is. And the highest available level to which an electron, a fermion, is populated is called the Fermi level. This energy is EF. So this is the Fermi level. Now this Fermi level could be a large energy. If you have a large number of electrons, this Fermi level could be large energy. So any energy, by the way, just effectively any energy, EF, can be written as AB EF. And this is not the real temperature of the sample. The real temperature of the sample is 0 kelvins. But the effective temperature of the fermions inside this well can be really large. This could be thousands of kelvins. Because this energy is large. If you have a large number of electrons, depending upon the spacing between these levels, this energy is continually going up, 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 up. So the effective temperature of the electron, which is called the Fermi temperature, is really large, even though the sample is at 0 kelvins. So the electrons are really, really energetic. So this is a gas of fermions. It's called a Fermi gas. In fact, it exists in nature. The electrons, the conduction electrons inside a metal have this structure. They go up to a certain Fermi level inside the valence band and the conduction band, inside the conduction band. So they are filled up to a Fermi level. Alright? It exists in white dwarfs. White dwarfs are kind of stars in which the electrons have these large energies. It exists, this kind of behavior exists in neutron stars because neutrons are also fermions and they occupy these energy levels. It's simply the Pauli exclusion principle that is pushing the electrons to higher and higher energies. If instead, I'm going to take questions, don't worry, I don't shy away from questions, but I don't want to break the flow here. If I have bosons, and I put bosons inside this infinite well, And if I'm actually really at 0 kelvins, then all of these bosons, no matter what the number of the bosons are, they are going to live clustered together in the ground state. All of them are going to live happily here. Birds of the same feather, they are going to flock together. At 0 kelvins, all of these bosons are going to live in the ground state. So if you have a material and somehow you can achieve a temperature, suppose this gap between two successive energy levels is delta E. And if you could achieve a temperature KBT, which is much smaller than delta E, if you could achieve such a temperature, then all of these bosons are going to coalesce, condense, gather together, crouch together in the ground state. Okay? This is also gas in which all the bosons are clustered together. This is called a Bose gas. Now let's take a short break and then we'll see what happens if we raise the temperature a little bit. Let's take a break.